Alright, so last but certainly not least in this unit, we're going to be looking at application problems with exponential functions, which mainly involves dealing with word problems. And I know that generally you haven't been a big fan of word problems, especially after quadratics, but hopefully you'll find these ones a little bit easier to work with. These calculations usually aren't as bad to work with. So just in general, just to remind yourself, if you're just looking at a parent function with no transformations, how can you tell if it models growth or decay? Growth will be again, if the function's increasing from left to right, so if you have a base that's larger than 1, like y equals 1.3 to the x, and decay will be if it's decreasing from left to right, with the base between 0 and 1. And that's key, okay, because we're going to have some problems that involve exponential growth, exponential decay. You need to make sure you're on the right track by making sure that your base is actually going to be making sure it models growth by having it be larger than 1, or models decay and having it be less than 1, because that's a really common source of error. So with that in mind, the basic equation that we're going to use to solve almost all of our word problems is going to be y equals c times a to the x. So you see that there's no horizontal shift, no vertical shift, just some sort of vertical stretch, some sort of c value, and then a to the x. So what I want you to do, there's a couple of graphs here, and you can see there's 2500 times 0.5 to the x, 1000 times 2 to the x, and then 5000 times 1.05 to the x. So in this case, you can see our different c values. We've got 2500, 1000, and 5000. So if you look at the graphs, well, what does that c value represent? Now, maybe a little bit harder to see on the sheet in front of you here, but you see that the 5000, our c value right here, happens to be our y-intercept, our starting value. Okay, 1000, again, the scale's not perfect, but looks like it's happening around there for our starting value. For 2500, same kind of thing, starting right up there. So this c value winds up actually being what we call our initial value, or the y-intercept. So if we know our initial value and we know it models growth, or decay, we can use that to help us solve whatever problems we can deal with. So in general, when we're dealing with this equation y equals c times a to the x, what do our variables represent? Well, we just said c represents our initial amount. Okay, a will represent it will be the base of our exponent, and it could represent growth or it could represent decay. And what matters is you have to make sure you know it's growth or decay, because there's going to be problems where to describe a rate of growth or a rate of decay. So if you're going to have a growth rate, like saying it grows by 6%, you have to add that 6% onto a base of 1, so you can have a base of 1.06. Okay, you can't just say 0.06 is your base if it's growing by 6%, because that would model decay, right? So you would add your growth rate to 1 if it's growing. You'd subtract your decay rate from 1 if it's decaying or shrinking. Okay, so then you just have your variables x and y. In general, x will be time or number of growth periods, and y will be our final amount, or our amount after a certain given time. Okay, so the other thing to keep in mind when you're talking about the growth rates and decay rates, they're often almost always given as percentages, so I always have to convert to a decimal value by dividing it by 100. Okay, and you'll see what we mean. Okay, but this basic equation, y equals c times a to the x, can be your starting point for just about every single word problem you're going to run into. Okay, so let's work a little bit with the base here. So determine the percentage change given the base. Let's say the exponential function, the base of the exponential function is 1.24. So already you know that if the base of your exponent is 1.24, this is going to represent growth. Okay, but growth by how much, right? So we know that in general our base is going to be 1 plus r, where r is this case, growth rate. So if we want to find out our growth rate, we just need to solve for r. So we know that 1 plus whatever our growth rate was equal to 1.24. Well, how do we solve for r? Well, it's simply a matter of subtracting 1 from both sides of the equation. So we wind up with r being equal to 0.24. So if we're adding 0.24 as a percentage, this would mean that r was equal to 24%. So what the base of 1.24 tells you is that you have growth by 24%. Okay, now let's take a look at one where it's decay. So again, you recognize here that your base is less than 1, so this is going to be decay. So if it's decay, 1 minus our decay rate will equal our base. So 1 minus r equals 0.81. Okay, so again, let's solve for r. Let's subtract 1 from each side, just like we did over there. So we're going to have negative r equals negative 0.19. And dividing both sides by negative 1, we get r equals 0.19. So what this means is, again, we have decay of 19%. Okay, so you need to be able to recognize whether your base is modeling growth or decay, and if you're given a growth or decay rate, you need to be able to get the base from that. Okay, and you'll see that when we do some problems. So here's a typical type of problem you might run into. So what amount of money would grow to $2,500 in 6 years if invested at 9% per year? Now, this notation here, 9%/A, what this really means is 9% per annum, which really is just a fancy way of saying per year. Okay, let's take a look at this. So again, it's an exponential word problem, so let's start with our basic y equals c times a to the x. Okay, we just need to figure out from the word, from the question, what goes where in the problem. So what we're told here is that we want to know what amount of money would grow to $2,500 in 6 years. So we don't know what amount we're starting with. Okay, that's what we're looking for. So in this particular case, what we're looking for is c. That's going to be our unknown. Okay, we want it to end up at $2,500. So if we want to end at $2,500, that should be our final amount, which is y. We're told it's going to take 6 years. So that would mean x is 6. And we're told it's invested 9% a year, which means the amount of money that we're gaining is 9% of our money each year. So if we're gaining 9%, okay, that means our growth rate as a decimal is going to be 0.09. So again, 9% divided by 100. So we're going to have to add that to get our base, add that to 1. So our base is going to be equal to 1 plus 0.09, which means our base is 1.09. Now again, this isn't one of these things you can just blindly throw numbers into equations and hope it works. Okay, you have to think. You can't just say see 9% and think, oh, I'm going to put 0.09 in, because that should ring true and ring false in your mind, because again, the amount of money is going to grow if you invest it, so you shouldn't have a base that's less than 1. That would model decay. Okay, so with that in mind, with everything we need to put in the equation, we should be able to start solving it. So I know that y is 2,500. Okay, c is unknown. My base is 1.09, and my x is 6. Okay, so how do I solve for c? Well, I just need to divide both sides by this 1.09 to the 6. Now, you can run 1.09 to the 6 takes 1.6 in your calculator right now, but you have to be extremely, extremely careful with rounding. Okay, because if you wind up rounding and you take something to 6th power, you wind up losing a ton of accuracy. So my strong suggestion is to not do anything in your calculator until the very end, until you have the variable isolated. If you must round, keep every decimal place in your calculator, because otherwise your answer will be so far off that I won't be able to accept it. I'll have to take marks off. So what I would strongly suggest doing is, before you run anything in your calculator, divide both sides of the equation by your 1.09 to the exponent 6. Okay, so those are going to cancel. You're going to be left with c is equal to whatever $2,500 is divided by 1.09 to the 6. And then once you get down to here, now run everything through your calculator. You won't lose any accuracy that way. Okay, so you should get $1,490. And since it's money, we'll keep 2 decimal places, so 0.67. Okay, and again, you got to be very careful with your rounding, so I would suggest waiting until the very end to run things through your calculator. Okay, so hopefully that word problem wasn't too bad. Again, as a general rule, you're going to start with y equals c to the x, and then try and figure out from the problem what parts of the equation you know and what parts you're trying to figure out. And in general, you should know 3 of the 4 values, and then you can solve for the 4th one. Okay, so let's take a look at another one. So this one wants to determine the annual interest rate to 1 decimal place, which allows an investment of $1,150 to be worth $1,306.95 in 4 years. Okay, so again, let's think about this and see what parts of the equation we know. So we're starting off with an investment here of $1,150, and it's going to be worth $1,306.95 in 4 years. So we already know our investment starts at $1,150, so if it starts at $1,150, that's going to be our C. We know it's going to end up at $1,306.95. That's going to be my final value, which is y. And we know it takes 4 years. So that tells me that I know y, c, and x. So what I need to figure out here is my annual interest rate, okay, which again is going to be added on to my base of 1, because again, this money is going to be growing from 1150 to 1306. So right now I don't know anything about my base except that it's going to be equal to 1 plus r. Okay, and when I'm looking for that annual interest rate is going to be the r right here. Okay, so it's my growth rate. How much is my money growing by from year to year? Okay, so again, let's start by writing out my equation. Y equals c times a to the x, and put in everything I know. So I know I am going to end with 1306.95. Okay, I know I'm starting with $1,150. And my base is something going to be 1 plus r at this point, and I know that my x, my number of years, is going to be 4. Okay, now again, I have everything here. What's tricky about this one is the variable to solve for is not as easy to solve for. It takes a little bit more algebra. So if I'm trying to isolate something inside this bracket here, in terms of the algebra I need to do, I can't take the 4th root yet. I can't get rid of this exponent because this 1150 doesn't have the exponent as well. So what I'm going to have to do here first is divide both sides of the equation by 1,150. Okay, and again, I'm not going to run that through my calculator yet because I don't want to lose any accuracy. So I'm just going to leave it as a fraction right now. Okay, so it's a step closer. I'm still looking to get r by itself. What I need to do now is get rid of this this power of 4. So the way I'm going to do that is by taking the 4th root. Okay, remember I can undo a square by doing a square root. I can undo an exponent of 4 by doing a 4th root. Okay, so this is now going to give me the 4th root of whatever 1306.95 over 1150 is. And again, don't round now if you can avoid it. Okay, just leave it in your calculator as long as you possibly can. And that's going to be equal to 1 plus r. Okay, let's just make some room here. Okay, so the only thing left now to isolate r is to then just subtract 1 from both sides of the equation. Okay, I know the left side of my equation is starting to look very, very ugly, but again, it's all just something I can run through my calculator. It's all just numbers over here. So I get whatever the 4th root of 1306.95 over 1150 is. So I do that first and then subtract 1. Okay, so all this is something you should be able to run through your calculator, and when that's all said and done, you should be able to get the value of r by itself. So try and run that through. Let's see what we get. So I get approximately 0.0325 for r. Okay, and that's as a decimal. If I want it as a percentage, you need to multiply it by 100, which gives me 3.25%. Okay, so again, the idea is still the same. We still knew 3 of the 4 values in the equation. We just had to solve for the 4th one. And again, it's just a matter of using algebra to get that last one. Okay, hopefully that one wasn't too bad. So here's another one here. So card depreciates by 7% each year. If it's worth $56,000 new, how much it will be worth in 9 years? So what I'd like you to do here, I want you to try and set this one up on your own first. So at the very least, I want you to be able to tell me what y, c, a, and x are, what values you know, what you're looking for. And the big thing to notice here is that it says it depreciates by 7% each year. If it's depreciating, that means it's losing 7% of its value each year. So think about how that's going to affect how you deal with the base of your power. Okay, so give that a try and set it up, and we'll go through it together in part 2 of the lesson.